Chapter 10 is our first foray into the very large statistical topic of hypothesis testing. Hypothesis testing is very, very important. It's something that we will be spending all of Chapter 10 on, most of Chapter 11, and if we continue on Chapters 12, 13, etc., it would be all full of hypothesis testing. So this is going to be a very big deal and a very big concept. And what's more, when we actually run hypothesis tests, they're going to be very large and with a lot of steps. So let me show you what a hypothesis test paper looks like on your Gold Notes packet from the back of your course pack. So you can see this is going to be a long process with a lot of steps to it. And so in 10.1, what we're going to do is we're going to get into the nitty-gritty of some of those pieces of that larger process. We're not actually going to perform the larger process. We're not going to do the full hypothesis test yet. That we're going to save until 10.2 and 10.3. But currently in 10.1, we're going to learn about step 1 right here. We're going to learn a little bit about what alpha really means, which is step 2, and then we're also going to learn how to write conclusions, which is step 6. And you can see the step 1s have certain properties as we continue. Alpha is always there for step 2, and then step 6 always is talking about stating conclusions. So that's what we're going to get into in chapter 10. But in 10.1, we want to talk about some of the pieces and components of that. But before I do any of that, I want to spend some time building up the idea of what a hypothesis test is. So in class, my students will be given a 6-sided die, and they're asked to roll it 12 times. And they're going to count how many 5s they got total. So if they rolled the die 12 times and they got 1 5, or they rolled the die 12 times and they got 3 5s, that's what happens. So when I rolled the die, I got 2, right? So I rolled 2. You can feel free to roll along if you so desire. But I'm going to pause this. I'm going to give you the data set that I got from a particular class. So 1 second. So when I did this in class, I had 2 people have 0, 4 people had 1 5, 10 people had 2 5s, 7 people had 3 5s, and so on. And I know what you're thinking, 4 5s, 1 with 5 5s, and 1 with 6 5s, and you're thinking, well, they'll all be zeros from then on. Oh, but you'd be wrong. There was one student that raised their hand and said they had all 12 of them 5s. Okay, so that's interesting. Let's think about that for a second. You're rolling a die over and over and over, and every time you got a 5. So what are some conclusions we could jump to about this student? Let's call this student Steve. So what do we think about Steve's results? Well, at this point, we need to think back to chapter 8. It could be that there was bias somehow. It could be that there was a fluke, or it could be that the parameter that we assumed was incorrect. All right, so bias sample, we learned that in chapter 8. Fluke, right, by random chance it just happened, or the parameter was wrong. Something is up with the die, and the parameter that we assumed, which is that p is equal to 1/6, was not correct. All right, now what kind of evidence do we have? Well, if he's lying or cheating or something like that, then there's not really much we can do about it. So, I mean, a bias sample creates bigger problems for us because we really can't deal with it mathematically because the person's just lying. So we kind of knock this one out and just say that's impossible, even though in real life, of course, it is possible. That leads us to making a choice between fluke and something is going on. So we want to think about this 2 ways, and this is an idea that we're going to come back to over and over and over and over again. So you want to keep this example in mind for future. We know that something is up. We don't know, but we assume or presume something's going on with his die because he's so far away from all the rest of the students. All these zeros in here mean that he is far, far away. He's an outlier. Now, how do we determine how much of an outlier he is? Well, I mean, it's all well and good to say he's an outlier, which he is, but we could get a little bit more formal about it than that. We could actually find his z-score. So just notice real quick that this is a binomial experiment. It's a binomial experiment with n equal to 12 and p, the probability of success, equal to 1/6, or at least assumed to be 1/6. Well, if that's the case, then the mean would be n times p, which is 2. We learned that back in section 6 too. And that's why, in case you'll notice, the 2 line has so many students there, because that was actually the value we'd expected to have. All right. But then the standard deviation, we had a formula for that as well in chapter 6, which was that sigma was equal to the square root of n times p times 1 minus p, which is the square root of 12 times 1/6 times 1 minus 1/6, which is about 1.2191 on a calculator. So that means that we could find Steve's z-score. Z-score, remember the formula we learned way back in chapter 3. It is x minus mu over sigma. So his x value was 12. He got 12 fives, minus 2, which is what we expected, divided by the standard deviation, gives you a z-score of 7.75. 7.75, which is a very, very high z-score, right? He is very unusual. He's very far away from the rest of the group, and we just proved it with the z-score. So the z-score will be how we prove that classical method. Okay, now the other way we could spot that he has a weird die, that something is going on, right? That the parameter that we assumed, which was that 1/6, right, the probability of 5 is 1/6, is not like what we thought. And that is that the chances of him getting what he got by random fluke is very, very low. So if you go back and look at your options and say, okay, we knock out that he's lying. We just have to assume that that's not the case, because if it is, we've got problems. That leaves you to these two. So you can say, well, he's far away from the rest of the group, right? That's kind of something's up. Or we could say the chances of that fluke are really, really, really low. If that's the case, then if it's really, really, really low, then it's probably more likely that the parameter was wrong in the first place. Now, how low is low? Well, this is binomial, so we actually could find it, right? The probability of 12 fives, let me type this up real quick. There we go. The probability of 12 fives I found with binom PDF on the calculator. So 12, 1/6, 12 is 4.59 e negative 10, which is this number, which is extremely, extremely low, right? That means that it's probably not a fluke. It's more likely that something's going on with his die, i.e. that the parameter is wrong. Okay, so keep in mind these two ideas, because we're going to use them both all the time. The classical method is using a z-score. It's saying his z-score was far away from the rest of the group, and you can say it because his z-score was very, very high or very, very low. Very, very large, I should say. Right? A very, very large z-score. Being more than 2 or 3 standard deviations away from the mean is a sign. The other way to see it is that the probability of that fluke, that random chance, it could happen, but it's very, 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 very low. Right? And that means it's probably more likely that something else is going on. It's probably not the fluke. It's probably that 1/6 that I assume to be true for all these dice is probably not the case. Now, is it possible that there was somebody else in the room that had a die with no fives on it? And the answer is yes, it was. There was a student. There was a student, Andrea, who had no fives in the class. There we go. We didn't catch her because we didn't have that evidence to support the claim that her probability of 5 was not 1/6 for her die. Right? She was hiding amongst the other 0. Right? So there was 2 people up here. One of them had a rig die. One of them didn't. And the problem is that 0 was not a rare outcome. Actually, I'll change it. So we didn't catch her because 0 was not a rare enough outcome, so we didn't know that the probability of 5 was not equal to 1/6 for her die. Right? We didn't catch her. She didn't have a rare enough outcome, unlike Steve, who had a very, 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 very rare outcome. So to catch her, what we would need to do is make n larger. We would have needed to roll more than 12 times. If we rolled 100 times, we would have spotted her, because she would have been the only student still sitting at 0. And I just added that in. So if we'd rolled 100 times, we would have known about her, because then she would have been the only student at 0. But we didn't roll enough. We didn't have a large enough n, so we didn't spot her. And so this possibility, the fact that when we make a decision, there could be people slipping under the radar, that's an important idea for us. right? That leads to one of the possible errors that we could have. So we want to keep this in mind that, well, first of all, we don't know for sure Steve's die was rigged, right? But even if we didn't have Steve in this group, even if there was nobody at 12, it doesn't necessarily mean that all the rest of them are not rigged. It just means we didn't have evidence for it. And that's going to be very important to us.